He has worked in civil and geotechnical engineering projects, both in UK and abroad. So Demos, once again, thank you for joining the webinar and handing over the platform to you.
Thank you, Sharav. I would like to take this opportunity and thank the Tunneling Association of India young members for inviting me to give this talk. So today's presentation will be a general talk on the challenges in drill and blast tunneling in Hong Kong. And I will focus on a project that COVI has designed and since then has been built in Hong Kong. A brief outline of the presentation. I will give a small introduction just to make sure that everybody knows a few things about Hong Kong. Then I will give some background information about the project that we designed. I will discuss a bit in more detail about the design aspects, design elements of a drill and blast tunnel. That will be followed by some lessons learned. Then I will discuss about a couple of value engineering exercises we undertook on this project. And I will close this presentation giving some photos from during construction. Just to give a bit background information about Hong Kong. So Hong Kong is on the southeast part of China, which you can just about see here in this small dot. And then this is a zoom in which highlights the area where Hong Kong is. It shares land borders with China, and that's the Hong Kong mainland. And this here is referred to as the Hong Kong Island. Hong Kong has been in the past a Commonwealth country, and then in 1998 it was handed back to China, and since then it operates as a special administrative region. Since then, China wanted to invest heavily in Hong Kong and create the infrastructure so that Hong Kong becomes a gate to the West. Here I have also added some photos from Google Maps where you can see how mountainous the terrain is in Hong Kong here in this area, and how difficult it is then to build all these big infrastructure projects. With this slide, I would like to make a comparison between Hong Kong and London, which have approximately similar population. In terms of an area that Hong Kong occupies, this is approximately 2/3 of that of London. However, the developed area in Hong Kong is only about a quarter of that on London, and the main reason for that is due to the mountainous terrain that I referred to in my previous slide. And due to that reason, the density in Hong Kong is about 5 times more compared to that of London. On the left-hand side, you can see a photo from Hong Kong with all these high-rise buildings and how that compares with on the right-hand side with the photo from London. And another interesting statistic for Hong Kong is that more people live in these buildings above the 14th floor than any other place in the world. Some background information then about the project that I will discuss today. So here in this photo, you can see a part of Hong Kong. Here in the north is the border with China. The red line is the 26-meter long express rail link. This is the new line that was proposed a few years ago. That's 26 kilometers in length. It's within the Hong Kong area, and that was split in 9 contracts. Our contract lies between the 2 villages of Nau Tam Mei in the north and Tai Kom Po in the south. In between these 2 villages, there is a hill about 350 meters high. The contractor for this contract was a joint venture between Kier, Caden and OSA, and Covey has been appointed as a contractor's designer for this 2.6 kilometers length of the contract, and we were responsible for the design of the permanent and temporary support of the tunnels, but also the design of the temporary support of the shafts. Here at the bottom, you can see a long section along this 26 kilometer length of this proposed new rail line. And our contract, the 2.6 kilometers that I will discuss today, is in this area. And you can see this mountainous hill that we were asked to design below. Now, this project is part of a wider project of the Chinese government that they want to invest in the infrastructure and improve the infrastructure. And therefore, they decided to build a new express railway link connecting Guangzhou, which is a city in China in the north, with West Kowloon in Hong Kong area. And the aim for that was to reduce traveling time between these 2 cities from currently 100 minutes down to 50 minutes approximately, and also increase the capacity of passengers. The current line that takes about 100 minutes to travel between the 2 cities, you can see here with the black line, and the new express rail link you can see here with red line within the China, and then with the blue line is within the Hong Kong area. This slide here shows schematically the geology and the topography for our contract. As I said previously, we had to tunnel 2.6 kilometers in length under this hill, which was a maximum of 350 meters cover. In the north, we had to design and construct this 90-meter deep shaft, which is called Nau Tam Mei. And in the south, there was a 40-meter deep shaft, which was called Tai Kom Po. The drift geology consisted of alluvium and completely decomposed tuff, which you can see with these light colors here. And then with this green color here, you can see the solid geology which consisted of strong to extremely strong tuff. Because of the geology, how good the rock was, and the topography, the 350 meters of overburden, it was decided that the most appropriate method of construction was drill and blast, and that a TBM was not appropriate in these ground conditions. This photo now shows the site in the south, in the Tai Kom Po shaft, the 40-meter deep shaft, looking north. And this is the 350-meter hill that we had to tunnel through. So that's looking north. The other thing to note here is that there aren't any roads here, so there's no easy access to get drilling rigs in order to drill boreholes and extract ground information for this area. And for that reason, the ground information we had, the borehole logs, were very limited. In this slide, I will try to explain very briefly a typical cycle of the drill and blast advance. So for this project and for these ground conditions, we typically had between 5 to 6 meters of advance lengths for each cycle, with the aim of advancing approximately 40 meters within a week. So the first part of the cycle consists of drilling some holes in the face of the tunnel. so that in the next phase you put some explosives and detonators and you charge these explosives. The next part of the cycle is the actual blasting. So I will show a very short video about that. This is a video from another contract, not from our contract, and it shows a blasting of a bench. What that is, so typically when you excavate a tunnel, it's full face excavation and you blast the face. But in some cases, you may have the face split into two, the top heading and the bench. So what you will see in this video is the blasting of the bench. And before the blasting, you need to make sure that all people working underground either evacuate the area or move to a position of safety. So hopefully this video will play. Yep, so hopefully you all saw that. So initially you saw the detonation and then the blasting. The next part of the cycle is to the ventilation. So you need to bring fresh air in the face and remove all the particles that might cause any health problems to the people underground. So you need to bring good quality air in the face. This then is followed by marking, so you need to remove all the blasted material, the blasted rock, and that can take, it's a big task and can take anything between 6 to 10 hours to remove all this rubble. The next part of the cycle is to do the scaling, so you need to make sure that you remove any loose blocks that may fall prior to installing the support, and therefore for health and safety reasons you need to do that. And as you notice from this photo, this is done from distance so that you are not supposed to do this in an area where the support has not been placed, has not been installed. Once scaling is finished, then people can move closer to the face, but always below an area where has been supported so that they can do the face mapping and the survey and decide what support needs to be installed in the blasted area. And the last step of the cycle is to install the support, which typically for a drill and blast tunnel, this consists of rock bolts and sprayed concrete. And that's the last part of the cycle. And then the next cycle, the next advanced starts. For this project, the client indicated that they would want to have a permanent lining as well. For this to happen, obviously, you need the temporary lining to be installed first to provide a safe environment for the workers to work underground and install the permanent lining. So this typically for a drill and blast tunnels, now what that consists of, this support is the primary or temporary support, which as I mentioned previously, it's sprayed concrete with rock bolts, which is, you can see here in this area, the sprayed concrete. Then this is followed by typically with a waterproof membrane in this project. In other projects may be a sprayed membrane, assuming that there is water underground. If there's no water, it's completely dry, obviously you don't need to install that. And then you can see the permanent lining installed in the end. And on the right hand side is a detail from one of our drawings detailing the 3 different elements that I just described. In this slide, I'm showing in plan view the 2.6 kilometers of our contract that we had to design. This is the shaft in the north, and this is the shaft in the south. I have cut this in 3 elements because it wasn't easy to put the whole line in one go. So what we had to design was two, as I said, mentioned previously, two shafts. The now TAI shaft in the north, which is 90 meters deep. The TAI Compo shaft, which is 40 meters deep, and that is in the south. So these two shafts demark the extent of our contract. We also had to design a crossover cavern, which initially during tendering process, this was located in this area. And during that time, we undertook a big value engineering exercise to demonstrate the benefits of moving the cavern closer to the shaft. I will discuss about this later on in this presentation. Another item we had to design was the twin bifurcations, and what I mean by that is you can see that you have 4 consecutive enlargements of the tunnel profile. So at the end, at the largest span, that can host a second stub tunnel to accommodate a future extension of the line. The main element, design element we had to do was the single track running tunnels, which ran for 2.6 kilometers. But because these were twin tunnels, as a matter of fact, it was almost just over 5 kilometers length of tunnels. We then also had to design the so-called Plenum Tunnels, which were the tallest and largest tunnels, and these were used for ventilation purposes to bring air from the shaft into this cavern and the other way. I will discuss about this in more detail later on the presentation. We had to design cross passages every 250 meters, which you can see here schematically. And the last design element was a sump pit to collect the water underground during construction, which was here in this area. In this slide, you can see the different profiles we had to design, which, as you can see, there are quite a lot. And then if on top of that, you see that for each of these profiles, you had to design different support types to accommodate different ground conditions. That will become clearer in the following slides. You can see how big the task was to design for these tunnels. These 4 profiles are for the bifurcations, which, as I mentioned previously, are the 4 different enlargements in profile, so that then at the end, at the largest part, they can accommodate 2 tunnels, 2 single track profile tunnels. This is the big cavern that we did the value engineering exercise, and we had to move then closer to the shaft in the north. These are the Plenum tunnels, the tallest tunnels that we had to design. Their main purpose was for ventilation. These are 3 different profiles of the single track running tunnels. This was the typical profile, and then these 2 are some small enlargements. And finally, these are 3 different profiles for the cross passages. So in the following few slides, I would show you some photos of each of these elements so you can understand the size of these excavations. So the first photo here shows the 90-meter deep shaft in the north, the now TAI shaft. On the right-hand side, you can see a 3D schematic of this shaft. This had a very strange shape. And we were responsible for the design of the primary temporary support. We weren't responsible for the permanent lining, so we had the constraint that we had to follow this profile, this shape. You can see at the top it's a circular cylindrical shape, and halfway through there is a bell out that then changes the profile to a rectangular. The circular part is about 40-45 meters, and then the transition plus the rectangular box another 45-50 meters depth. So overall it's 90 meters depth. On the right hand side here, this small dot is in scale a 2-meter high person, just to show you in scale how big this shaft was. What you can see here in this photo in the middle is a photo from a ground surface looking down the way the excavation, and you can see that up to this point the shaft is being supported by these piles, and we weren't responsible for this support. Our responsibility lies below these. These piles were used to support the overburden material, so the soil. So that's the transition here, the end of the piles, the transition from soil into rock. And as you can see in this photo there, the support of the shaft in rock then consisted of sprayed concrete and rock bolts. And here at this point is where the circular part of the shaft finishes, and then the bailout starts. And in this photo is at the bottom of the shaft, 90 meters deep, looking up the way. And you can see this part here that's supported by the piles, which was not our responsibility. Our responsibility started from this collar. So you can see the circular part, the cylindrical part of the shaft, and then the transition, and then the bottom part, which is rectangular in shape. This is the other shaft in the south, the 40-meter deep shaft, and you can see a similar arrangement. You can see some piles here to support the overburden in soil, and when the transition between soil and rock is, that's where the piles terminate, and that's where our COVI's responsibility starts. So we were responsible to provide the support of the shaft in the rock here. Now, I've said that this is a smaller shaft, only 40 meters deep compared to the other shaft in the north, but still you can see that this is like a large excavation, approximately 14 meters by 28. In this photo, you can see the single track running tunnel profile, which, as I mentioned previously, it runs for about 5 kilometers in length, 2.6 in its direction. This was one of the smallest profiles we had to design, almost circular in shape for a better redistribution of the stresses. You can see the support, which again consists of the sprayed concrete. And as I said, even though this is one of the smallest profiles we had to design, you can see that it's a fairly big excavation if you compare it against the people mapping the face here. In this photo, you can see the bifurcation. It's the largest of the 4 profiles. So schematically, as I mentioned previously, the bifurcation hosts 4 different consecutive enlargements. So what you can see in this photo is the last enlargement here, where it needs to host 2 different tunnels. So this is the single track running tunnel. And here it will be built the short stub tunnel to accommodate a future extension of the line. This photo shows the cavern, the big cavern, which is close to the shaft in the north. This is a 3D schematic up here. So this is the deep shaft, the 90-meter deep shaft, and this is the cavern. And these are the 2 largest excavations in our contract, and these are the tall plenum tunnels for ventilation purposes that connect the 2. The length of this cavern is about 115 meters, and at the time of construction, this was one of the largest caverns in the Hong Kong network. Here in this sketch, you can see how the cavern profile, which is this, along with the 2 single track running tunnels, compare against some typical tunnel profiles in London. So on the left hand side, this is the crossrail profile, is the new Elizabeth line. It's not exactly to scale, but it gives you an indication on the magnitude. And this is the old London Underground tunnels. It just to show the difference in the magnitude of the excavation. So this slide shows how these excavations compare against you know, for instance, the Big Ben is about 90 meters deep, the same depth as the shaft in the north, and the length of the cavern compares with a football pitch. So again, that's another indication of the magnitude and size of these excavations that we had to design. In this photo, you see the Plenum Tunnels, which, as I said, connect the shaft in the north with the cavern. You can see schematically here in plan view. So it's these tunnels connecting the shaft with the cavern. These were the larger tunnels we had to design in this area. So you can see the height was about just under 14 meters and a span of just under 11. And the biggest difficulty we had during the design was to make sure that this slender pillar, which is very thin and tall, is not overstressed, which that could pose a health and safety issue during construction. And again, just to get a feeling of the size of these tunnels, these excavations, you can compare it against the size of that person sitting just below this opening. I will discuss about that problem in more detail later on, but that was one of the big drives of the value engineering exercise of having to move the this cavern closer to the shaft to reduce the length of these large tunnels and therefore reduce the risk of this overstressing, this pillar being overstressed. And the last design item, it's the cross passages. So here you can see the two single track running tunnels running in parallel, and the cross passage here. As I mentioned in one of the previous slides, we had to design these every 250 meters in our contract, and the main purpose was to assist during construction, but also in case of any emergency. On the right hand side, you can see a typical drawing, a typical detail of these cross passages in plan view and a cross section. So moving on now to the design elements, the design parts of a drill and blast tunnel. So I will briefly discuss the process of the design. So initially we need to gather all the available GI information with regards to boreholes, lab tests, in situ tests, and make an assessment of the ground conditions, create our own geological model, derive our own design parameters. So from then the borehole logs, we can also get information about the joint sets, the discontinuities in the rock mass, and we then do a statistical assessment of the joints so that we come up with the most dominant joint sets, and we do then the design based on these dominant joint sets, which typically can be like 3 to 4 or 5. In this case, we used a software called DIPS to do this. We then use an empirical rock mass quality method, which is the Q method, to derive to come up with an initial support for these tunnels. This would then be followed by an assessment of the potential of failure of discrete blocks. We, for this purpose, would use the unwedged software and see whether the support we derived from the Q method is adequate to support the potential wedges around the profile of the tunnel. We would then undertake numerical analysis to verify the support that we initially derived from the Q method or refine that. And we would also do then the standard time assessment using this empirical method by Wieniawski. We would have to do all these items for each of the design elements in our contract. One of the biggest tasks we had to do was to do this numerical modeling for these elements. And an initial question the designer has to ask is if the project is in rock, if the ground conditions are in rock, whether they need to undertake a continuum or discontinuum approach. So what this slide is trying to demonstrate is that it's not a simple thinking for that. One needs to consider the network of discontinuities relative to the size of the opening. But in most cases, if your project is in rock, then you would have to undertake a discontinuum approach. On the right-hand side here, what I have is an output from UDEC of the same tunnel excavation. And the top, this is modeled as a discontinuum. So in this block here, I have generated a network of joints. Whereas in the bottom, I've done the same analysis, but this time this is modeled as a continuum without joints. For ease of reference, the scale in the contours are the same. And what you can see here at the bottom at the continuum approach is that you can see how the major principal stresses nicely arch around the excavation. So that's the arching effect. Whereas here in the discontinuum approach, you don't see the same distribution of the stresses because you have the joints, and therefore the stresses try to follow the orientation of the joints. So you can understand by looking, compare these two, that there will be different support requirements compared to the stress distribution and whether you adopt the continuum versus the discontinuum approach. In this slide, there is a similar comparison, but this time you can see the displacement vectors. On the left-hand side, it's the discontinuum, and here you can also see the network of the joints that have been generated for this output. And on the right-hand side, it's the continuum approach without any joints, so you don't see any joints here. And the scale this time is not the same, but what you can clearly see is that the roof is moving by the same amount around the roof of the tunnel in the continuum approach, whereas in the discontinuum approach, the maximum displacement occurred in the areas where you have some loose blocks or the orientation of the joints is such that the blocks want to slide into the excavation. So you can see in this case, in the way the joints were generated, that happens here. In either side of that area, it's significantly less. Whereas in the continuum approach, you can see how uniform the displacement is around the roof. And again, depending on which approach one decides to choose, then it will come up with different support requirements. So how we did that? How did we end up creating a joint pattern in the software we used, which was UDEC, and make sure that what we generate is realistic? So initially what we did was to interrogate the 3D televiewer data, which is that. So here you can see a 3D of the borehole, and these planes indicate the orientation of the joints. So we get these data from the televiewer data, and we import that into DIPS to come up with the most dominant joint sets, as I described previously. The next important step is then to do a block size assessment, as it's called. So you want to create sizes of blocks that are representative of what happens on site. One thing to be aware of is that because this is a 2D analysis, one needs to work out the apparent dip for these joints and not just input the dip and dip orientation directly from the televiewer data. And the way to see that is that if you take a slice of this along this plane, that would indicate that the sliding plane is in this direction. Whereas if you take a section along this side, the sliding plane would be along this direction. And then the reality is, if that's the joint network, that the blocks will slide differently in different directions. So you need to make an assessment how best to model the wedges in a 2D analysis. So after creating the network of joints in UDEC, we would then extract this information and we would do a normal distribution analysis. So that would indicate what's the sizes of the blocks that we have just generated. We would then find the 50% of these blocks. Where would that lie? So the 50% of would give you here on the horizontal axis a typical size of block of, X. And we would then have to compare that against the size of the blocks that we would derive from the block size assessment from a particular borehole. And that's shown here indicatively by this hatched area. So if the two would be close enough, it would mean that our calibration is sufficient, and then we would have high confidence that what we're trying to model there is accurately represents reality. A few words about the Q system. So this was first introduced in 1974 by Barton. This is a rock mass quality assessment, and it's a mean of defining a support for a tunnel and an underground excavation. So what you see here on the bottom is the rock mass quality index, which is given by this equation. I won't go into the details explaining what that is. You can find more information on the web if you download this handbook from the Norwegian Geotechnical Institute. It's freely available online. And just to say that when the Q is higher, so as you move to the right hand side, it means that the rock is better. When the Q values are lower, it means that the rock is worse. On the left hand side, it's the span of your excavation, like the tunnel. Here in the top, you see some numbers there that would indicate the spacing of the bolts. On the right hand side, vertical axis, you can see the requirements for the bolt length, the minimum requirements depending on the span. And finally, here you can see some numbers, 2, 3, 4, 5, and that indicate areas which would give you an approximation of what the lining thickness should be, the spread concrete lining thickness. So we use that system to come up with an initial support for our tunnels, and I just give an example here. We came up with different support classes, and each of these support classes would have different ranges of that Q value. And here you can see what are the support requirements for the class 2B, which is a Q of ranging between 1 and 2.5, and then class 3A. So two adjoining support classes, and you can see how much different the support requirements are. And then you can imagine how much even more different would be the support requirements if you compare class 1A to 4. This slide shows how the Q chart was initially when it was first published in 74, and then later on the 3 major updates. And this is what is currently being used. Moving on to the lessons learned. So very briefly to say that as every method, this chart also has its limitations. So on either side, on the two extremities of this chart, what I would say is that there's no guidance after this area when the Q value is more than 10, what the bolt spacing should be. Now, typically you don't get bolt spacing wider than 2.5 meters, because then you don't have the composite effect. It's as if it's a spot bolt. So maybe that's the reason why, but there's no guidance as to like what to do in this area. And then similarly on the other side of the chart, where the rock is very exceptionally poor as described, there's no guidance as to what to do, what's the bolt spacing. in this area. Again, typically you don't put bolts closer spaced than 1 meter, but there's no guidance. Previously, I also mentioned that there are these areas, 4, 5, 6, 7, 8, that you can come up with the lining thickness. So if the requirements are within zone 5, for instance, you know that the lining thickness should be between 90 millimeters to 120. If the support requirements are within zone 8, there is no guidance as to what the support requirements is other than the bottom line in that zone indicates a lining thickness of 250, but there's no indication about the upper requirements. So it's down to the designer. So I think that's a limitation, that we shouldn't be using that chart if we need to support something that falls in this category. What we found when using this was that because this is an empirical chart, it's based on case studies from the past, and most of the case studies were falling within this area, and that's where it's more useful. So just something to bear in mind, that if you have to design something and you need to design it, it falls in that area, then you have high confidence. If it's out with that area, then you need to perhaps do some other assessment and not just use this chart. Something very interesting. So with regard to the support pressure, so in the initial publication, the 74, this formula was introduced so that somebody can come up with an estimation of the support, the pressure, the support pressure in the roof. There was a note to say that this formula, the units for this formula was in kilograms per centimeter square, and not what we typically would use in KPA or MPA. Now, in a later publication, 2002, Barton then mentioned that if you want to have the roof pressure in megapascals, then you need to use that formula. So it's a conversion of the initial formula. However, later on in Nick Barton's webpage, there is a file which is not published in a journal or a proceedings publication, that mentions that this formula, which was published in the 2002 publication, has an error. And instead, if you want the pressure in MPA, you should be using this. So just something to be worried about. Another thing we found was if you're using the Q method to derive the rock mass stiffness, there are various formulas available, and I will just show an example to see the difference between the different methods, the available methods. So firstly, if you were to use the Serafim and Pereira equation of the rock mass, this is based on the RMR, which is another classification system, but then you have this formula to convert the Q into RMR. So for a given Q values, if you convert that to RMR and then use the Serafim formula for the rock mass, you end up with these rock mass stiffnesses. If, however, you were to use this Barton formula, where it correlates Q with rock mass directly without the use of RMR, and for the same Q values, you can see like for like how they compare. Now, one thing to note is that for the higher Q values, even though there is a 5-6 gigapascal difference for such a high stiffness value, that doesn't affect the design as much. In all likelihood, the tunnel could stay unsupported. But for lower Q values, you can see the magnitude of the rock mass stiffness is almost half, depending on which method you use. So what I would say is that when you're using these formulas to come up with stiffnesses, rock mass stiffness, it's always good to have also lab tests or other ground investigation information or published data from the same area that you want to design, so that you have a better understanding whether it's closer, to these values or that value. And the last of the lessons learned items is the stand-up time. So we use this chart from Wieniawski. On the left-hand side, what you see is the roof span, which there is some ambiguity as to what that is, whether that refers to the span of the tunnel in cross-section, or if that refers to the advance length in the longitudinal distance. But I'll come back to that. On the horizontal axis, it's the stand-up times, and then here this envelope plots the RMR values. So it's the alternative classification system to the Q. And just to give an example that if you have a certain RMR value, say 45, then you plot this in that region parallel to the black lines. And then if you want to design a span of 10 meters, say, for this RMR, then that plots here in this area where you say that you're in the area of immediate collapse, and that then the tunnel can be unsupported up to 1 day. So obviously this is not acceptable. So you want to reduce the roof span. So if you were then to reduce it down to 2.5 meters, you would be in this area, and you would see that in this area, it's in the area where almost no support required, and the unsupported, the stand-up time can be more than 1 week. So that's how that works. Now, as I said, there is some ambiguity as to what that is, but the intention is that this roof span is always refers to the advance length. So it's the longitudinal distance, not the span of the tunnel. Moving on to the value engineering. So we did 2 major value engineering exercises in this project. One was the reprofiling of the tunnel, which you can see here at the top. So initially, when we received the tender drawings, the shape of the tunnel was indicated by this white, tunnel profile here. Which what you can see is that was taller and with a smaller span compared to the reprofiling we did, and that reduced the height of the tunnel, but made the span a bit larger. But what we achieved in this way, we achieved a more circular profile compared to the tender drawings, which were showing more straight walls. And because of that circular profile, that assisted in the stress redistribution and less load transfer onto the tunnel, and therefore the requirements for the lining thickness reduced significantly. And as I say here, we managed to have up to 80% reduction in the reinforcement of the permanent lining because of that. The other, as part of that reprofiling, we also managed to come up with radii for the tunnels and for the shutters that could be used in multiple tunnels for this project. So you don't have to have different shutter profiles for different tunnels. But the main value engineering exercise was moving the cavern from its initial location during tender to this location. So the contract was awarded to COVI based on the initial compliant design, as it was called, when the cavern was here, but with the intention that COVI would work on the alternative design, moving the cavern closer to the shaft, and I will describe that in more detail, the benefits of moving the cavern here. So the reasons we decided to move the cavern was, first of all, that by moving the cavern from this location, which was 200 meters away from the shaft, to this location, which was only 20 meters away, we managed to reduce the length of the plenum tunnels, which are these tunnels, the tallest tunnels we had to design. And by the same time, we had to increase then the length of these tunnels behind the cavern, which were the single track tunnels. So straight away, you can see we had significant gains in the excavated volume. A byproduct of that, because you had to excavate a smaller volume, it means you had a faster construction. So this tunnel was excavated in full phase, whereas the requirement for that was in top heading and bench. On top of that, then there were less support requirements. So you can see with the gray hats, the requirements for the permanent lining. So you can see how much thinner that is in the single track compared to the plenum. And most importantly, we reduced the risk of having this overstressed pillar between the plenum tunnels here. If you remember, I showed you a photo showing how thin the pillar was between the tall tunnels. So overall, we provided a buildable, innovative, and safe design by moving the cavern to this location, and everybody was satisfied with the outcome of this exercise. Here in this table, you can briefly see the savings in the excavated material in the volumes. Some photos moving on towards the end of the presentation of the construction. So we had to come up with a fairly complicated construction sequence for the cavern. It was quite important for the contractor to excavate this quite soon, so then they would be able to have two teams tunneling from either end of the contract, tunneling in both directions. So it was quite important to tunnel through this cavern quite early in the program. So what that shows is after finishing the excavation of the 90-meter deep shaft, you then excavate one of the two plenum tunnels, you ramp up and you enter into the cavern at the top heading, and you start excavating a small pilot over the full length. So you identify the ground conditions in this area. Once you do that, then you start excavating the side drifts. So subsequently in the next stages, you can see the excavation of the side drifts. So you end up at stage 5, where you have fully excavated and supported the top heading. And then the next 3 stages of the sequence show just the excavation of the bench. Once the bench was excavated, then it was easy for the second team that was tunneling from the north to be able to progress, advance the excavation as well. A few photos showing the different construction stages for the crossover cavern. So here you can see where the full cavern has been excavated, and here you can see the temporary supports of the sprayed concrete being applied. Then you can see the waterproofing membrane. In the next stage, you can see the permanent support at the wall and the invert. And then finally, casting the permanent support in the roof. And in this photo, you can see the internal details, the internal walls, and the slab and the roof, which is you can see in this cross section how this looks like. A similar slide showing the construction sequence for the single track running tunnel. So here you can see the sprayed concrete being applied, the waterproofing membrane, some reinforcement that was required in junctions or in area of poorer ground conditions, and then the final permanent lining, and you can see how good job was done. A couple of slides here on the design, what was shown in the drawings, the modeling, and final construction, how it was built, and that's for the cavern here at the top. In the bottom, you can see the same for the single track running tunnel. At the top of this slide, you can see the sequence for the bifurcation. And at the bottom, you can see again the sequence, the drawings, the analysis and construction, how it was built of the plenum tunnels. One slide very briefly to show you the shutter, how it looks. And as I mentioned previously, we designed the radii of the tunnels to be such that part of the shutter can be used at different design elements. This slide shows some difficulties, let's say, during construction, how the conditions were. People here are trying to install the explosives for the next round of blasting within one of the two shafts, and you can see, the whole area is submerged with water. This slide is quite important for construction, mainly, and things that can go wrong in a drill and blast tunnel. This is a photo of a wedge failure from another contract in Hong Kong. It's not in our contract. But when we're discussing about wedges and potential wedges and the support that we need for wedges, you can see the size of that. That's nearly the full height of the tunnel. And you can just about see the length of the rock bolts here. And the density, it's only, a few of them. So you can clearly see that the bolts in all likelihood were not long enough, and they weren't enough in numbers either, in density. On the right hand side, this is from our contract, an image of our contract from one of the two shafts, and you can see the amount of water we had to deal with during construction. This is a short video to show you how much water was coming in from the rock. And this is a video to show you the pressure that the water is coming out from the face when drilling in the face. And this is from our contract, and just to see the pressure of the water coming out from the rock. And the last slide, just to give you a timeline of this project. So construction at ground surface started in 2010. The drill and blast operation started end of 2011, start of 12. There was a breakthrough in 2015. And then the tunnel with all the finish lines was completed in 2019 and has been given to public since then. Right, I would like to thank you for your attention, and happy to take any questions.
Thank you, Demos, for such an interesting webinar. The platform is open for questions. If you have any, you may go on one by one.
Hi, Demos. Ayush here from TAI.
Hi.
I want to ask a question regarding the last slide which you showed, where the water was coming with full pressure from the drilled face. So how the construction team tackled that situation and they stopped the water?
Yeah, so as you can see here, they're just trying to, there was a lot of a series of grouting, injection grouting happening during construction as the blasting was advancing. And obviously that's something that hadn't been dealt with at the time, but then later on in the construction sequence, once all the grouted fan was installed, then that was then it allowed the team to progress with excavation. So it was mainly with grout fans.
With PU grouting or with cement grouting only, Demos?
Sorry?
With the PU grout, some chemical grouting or only the cement grouting, normal?
I think it was a normal grouting, but I can come back to you on that.
Okay. Thank you.
Demos, we have one question from Sachin. He's asking what was the powder factor achieved? Also keeping the water in mind, which type of a commercial explosive was used?
Yeah, so I'm not aware of all these details. That was mainly like to the contractor to decide on these details. It wasn't part of our remit. But again, like I can come back to you if needs be.
Okay. He also has one more question. Was P wave velocity of rock taken?
Yeah, so when we did our assessment, we used these empirical formulas that I described in my slides. We also did like the P wave, the dynamic. We had some lab tests for the stiffness. I mean, and we came up with appropriate stiffness values for the different support classes.
Okay. Uh,
Do we have more questions from anybody?
I would like to ask one question, Dimos. In the starting, you mentioned that drill and blast tunnel and choosing the type of tunneling based on drill and blast or TBM, based on any ground condition. So, like, how? I mean, how do we choose it based on the ground condition? Whether
Yes. So in this case, as I said, because the rock was quite strong, it was in a remote place. It wasn't an urban environment, which it makes always difficult to blast if you're in a city due to vibrations and all these things. It's much preferable when you're tunneling in medium to strong rock to use drill and blast, because with a TBM then you have quite a high terrain wear of the cutting phase, and you need to stop frequently, replace the heading, which is not an easy exercise. So that's why typically in hard rock you prefer the drill and blast method.
okay. So if you don't have any, okay. So Wahid has one question. Wahid.
Yes, thank you for your explanation. First question is, what was your rock kind? Is it igneous or sedimentary? What kind of your rocks?
It was tough. So that's the geology, the drift and solid geology, and typically the rock was described as moderately strong to extremely strong, with a small degree of weathering. At depth, there were some shear zones, but only locally. We didn't identify any large areas of faulting or weathering, so it was quite good ground conditions.
Okay, thank you. And another question: you had different cross section of the tunnels. Okay, in this kind of the different cross section, have you calculate? My question is about the calculation in Q systems, because in a big cross section is different. Sometimes you excavated in 6 or 7 section in 4 big cross section, but after completion, this cross sometimes we have some convergency. And my question is, what is your calculation about this area? Because in a small cross section is not important, maybe convergency, but in big cross section is very important.
Yeah, so if I understand the question correctly, you're talking about if you have multiple headings on the same tunnel profile.
Yes.
Yeah, so we had that issue with the crossover cavern, and as I showed in the construction sequence, there, you had multiple headings, a small pilot, and then 2 side drifts for the top heading, and then the bench was also excavated in two side drifts. What we found from our assessment and what we've seen from monitoring during construction was that as soon as you excavate the top heading and you support the roof, then you don't have significant additional convergence or deflection, lining deflection when you come to excavate the bench at the bottom.
Yes. No, my question is about the calculation. You need different support system in this kind of the cross sections. Okay, but you know, my question is, in small cross section, support system is low, but for big cross section, you need a stronger support system. But,
yes. So
please.
yes. So what we try to do is to see what are the requirements, the support requirements for the big span, for the whole span, and we try to install that even when we were excavating the smaller phase. So we would install the support that our analysis and our assessment would indicate that we need to install when you excavate the full profile.
Mm-hmm. Okay, thank you very much.
We have one more question from Mr. Nagaraju. I think you are in mute, sir.
Yes, yes. Good evening. What
evening.
factors have you considered for final lining? And is final lining is done throughout the along the length or partly? And what is the thickness of final lining?
So as I mentioned in the presentation, we had two linings to install. One was the primary temporary lining, which the purpose was just to provide a safe environment then for the tunnelers to install the permanent secondary lining. And the thickness of that obviously varied depending on the opening. So the thickness was different for the smaller excavations, which was a single track, compared to the larger excavation that was the cavern, the big cavern. And also on top of that, the thickness varied depending on the rock conditions or the anticipated rock conditions. So we had the support classes, and for the better support classes, we had the thickness. And then for the worse support classes, the thickness of the lining would increase, but on top of that, we may had some reinforcement in the lining as well. So, and because it was so many profiles, the thicknesses varied, significantly.
Okay, what is the grade of concrete you have used?
The concrete grade.
Yes.
Yeah, that's I can't remember now. I think it might be C40, but I can't remember for sure.
Thank you.
Okay. So I guess, Dr. Demos, we have covered all the questions, all the queries. And if there are some other queries, you can post it to us. We'll get back to you through Dr. Demos. Thank you, Dr. Demos. Myself, Ayush Raj, Chair TAI, for giving your valuable time on this wonderful webinar. One of the most interesting webinar we have in the recent times. So thanks a lot. Just for the information of all the young members and all the members associated with TOM, in the coming week, we are going to share the newsletter and one of our blogs. So stay updated. We'll mail you all the details and stay updated for all the details regarding YTC. So thank you, Dr. Demos, once again.
I would like also to thank you for the opportunity that you gave me to give this presentation. And I'm happy to take any questions later on by email, and I'll be happy to respond.
Thank you. Thank you, Dr. Demos. All these webinars will be available on our YouTube channel. We'll provide all the links in our WhatsApp group. So you can have this presentation. You can view this presentation later also. Thank you, Dr. Demos.
Thank you.
Thank you, everyone.